now we go, I leave the floor to Serena Danti, that can make the presentation regarding biocompatibility to illustrate how we can use the slides that are on the website. So how they can be useful, no, for teaching or understanding biocompatibility tests. Please, can you share the presentation, Serena?
Sure. I hope, is it coming?
Yes.
Yes.
Okay, so I put in presentation mode. Okay. So I'm going to try to let everybody understand so this concept of biocompatibility, and in particular of the biocompatibility if we refer to skin. So as Beatrice mentioned, and also the other speakers, we are investigating materials for skin contact, and we aim these biomaterials to be biocompatible with the skin. So let's see what it means exactly. Oh. How can I go? No, there is the presentation disconnected. I think I will try again.
Try to share the screen, the desktop, so you can move in your computer using.
Yeah. So because this is, you see now the presentation,
yes,
no?
Yes,
But if I move, it goes to black. I don't know why. You see, it's at the end of the presentation.
Go on PowerPoint.
Yes. So it's better. I can live in the PowerPoint mode. What do you think? Can you see it in the same?
You share your desktop. We see your PowerPoint.
So you can. Okay, I share the desktop. Let's see if I can share the desktop.
So with the share button, you select desktop.
Okay, not the presentation. Okay.
PowerPoint.
So
it's better.
Do you think now it's okay? I'm not sure. Okay.
Yes.
Yes. Okay. Let's go to the second. No. Okay. So I let this in not presentation mode. So I think I can move better, and you can see what. Or maybe let's see if it went to the. Yeah, I think it went to the last. So maybe that is why it was not showing. Sorry for the delay. So this is the first. So you see it, no? Okay.
Yes.
So, yeah, so I also collected the work of several collaborators working also in INSTM in the University of Campania, close in Naples. So, so first I would like to share with you some important definitions about what is a biomaterial and what about the biocompatibility. So these definitions are the ABC, the basic for understanding the fate of any biomaterial, any device when it is in contact with the human body. And there are in the literature several definitions of these two concepts, so biomaterial and biocompatibility. But if you look at them, they are very complicated. So the scientific community of biomaterial scientists used to adopt these two definitions that were made many years ago, but they are very simple, very effective, and can be still valid. So it is important to define a biomaterial which is a non-viable, so not vital material, not an organ, but is used as a medical device. So it is intended to interact with the biological system. So what is important to remember of biomaterials is that they are not simply materials. They are materials which must interact with the biological system, so can stay inside the body or also in contact with the skin, with the outside of the body, because this is still a biological tissue. So the biomaterials, to be defined in this way, must satisfy specific requirements. In particular, a medical device is defined to treat a medical condition, which is a pathology. So materials that are used to be in contact with the human body without any pathology are not a medical device. So this is important to understand from the beginning, because for the skin we have several types of materials that can be in contact, materials that can repair the skin so they treat the medical conditions, and materials that just for example, make the skin better, or possibly they can just stay in contact with the skin, but they are not medical device. So a medical device must be certified, and the materials, of course, that interact with the tissue, so they can be or not medical devices intended for the purpose that they have in this specific application, and we will see some relevant examples. Moreover, the biomaterials for medical device must comply ISO standards. That is not the case of materials that are in contact with the human body but are not intended to be for a medical device. So if we go to the next slide, okay, no. So I don't know, this is not working. Okay, so I go back. I'm sorry for that, but I don't know why. Okay, so biocompatibility is instead, it is important to remember, is the ability of a material to perform with an appropriate host response in a specific application. So it means that we have to consider these two things: the appropriate host response, which includes the reaction of the human body to the contact with these biomaterials, that can be an immune response or a cell response, and also for any specific application we intend to have a time of this application. For example, you see here that a prosthesis must stay in the body for 10 years, while a catheter can be in contact with 1 week. So the biocompatibility of the materials involved in the application are intended for the time of the application. For example, maybe a catheter is not biocompatible for 10 years. So also the material must perform, so must be active and do what it is supposed to do in this time. In order to understand better these differences, I put some fakes, for example. So the titanium is a biomaterial, no? This is, it's not a biomaterial, can be a biomaterial if it is used in a medical device, and for this must be certified and so on. Titanium is a biocompatible material. Also, this depends, as we saw before, on the application. So, for example, in bone can be biocompatible if I use for an eye or for another tissue, can be less biocompatible. And also it depends on the surface. For example, it generates a different immune response. So these are all facts that are involved in the biocompatibility. So biocompatibility is a very complex issue, and it depends on the specific application. So if we take like a general look to the biocompatibility, we have different factors that for sure affect biocompatibility in a negative way. So if the material is toxic, if there is some bacteria on the material, so it's not well sterilized, if there is a stress shielding phenomenon, so mismatching of mechanical origin in the material device, and also if we can have like immune reaction. But if we so usually we perform materials that do not show this, but also we need to study the response of the tissue. So we have different generation of materials that were supposed to have different reactions from the body. They go from like they range from the last century until now. In the first stage, the biomaterials wanted to replace the tissue, so they need to be permanent biomaterial, and for sure they had like an immune reaction and a fibrotic encapsulation. Then we slowly pass across different generations, and for example, materials that have a control immune reaction that are biodegradable in the human body, for example, and also materials that are able to induce the self-repair of the tissue, that are the materials of the third generation. And this material, they want an immune reaction, but a good immune reaction that is suitable for the purpose. So there are several factors important to understand. So also the regulatory institute, the body, they consider still a good definition of biocompatibility if a material generates a fibrotic capsule, because they refer to the first materials. But now we have a lot of evolution in this topic. So the most important is to control the reaction that happens when the material is in contact with the skin. And here you can see in this picture what can be the end fate. We can have both pro-inflammatory or anti-inflammatory reactions. And it happens like a cascade of events that involve different cells. For sure, we have the absorption of the protein on the surface. Then there are immune cells that go to check what is happening. And then if these cells have a bad reaction, like the macrophage you see here, then they secrete cytokines, so these molecules that promote inflammation and call back more immune cells to go and check and possibly try to expel the material that is not liked. Or the same cell can produce some good molecules like the one you see here, so they activate an anti-inflammatory reaction. And in the end, you see that there are other cells coming and trying to colonize the materials. If the reaction is too much strong, the materials is covered by fibroblasts and they generate this thick encapsulation. So this is something that we don't like to have. No, we like to have a material in a good contact with the skin. So inflammation and healing are two sides of the same coin. For sure, we need some inflammation because it activates a cascade of phenomena that can heal a wound, for example. But we don't want a high inflammation or an inflammation that is not going to drop down and it stays for long and become chronic. So what we like to have is anti-inflammatory or immunomodulating reaction. That means that after a first reaction, the body is accepting the material. So if we go on the skin, you can see here, the skin is a very interesting tissue, is an interface with the environment, so it is a barrier to defend our organs. And by this reason, it is for its nature, it is prone to give reaction because it wants to defend the human body. So there are different layers in the skin that we can see here. So we have the most outer layer, the epidermis, that is a compact layer. So, and then we have other layers. They have different purposes, and there are different cells. So it is being the first line of for protection of the other tissue, we have stress in the skin, and the stress generates inflammatory response. And because now in our time there are several chemical substances around, the skin is more prone to have a reaction. Sometimes it's an unwanted reaction or hyperreaction. There are many chemicals that generate reactivity in and allergic states in the humans. So it is important to check the biocompatibility not only of the medical devices, but also of other materials that are in touch with the skin. In particular, for example, Beatrice reported about the plasticizer. These materials can migrate out of the polymer, so it's important that we have to check what happens when these low molecular weight molecules are coming in contact with the human body. So here you see what the skin can do. So the skin can activate this inflammation, but also can self-defend, because the skin possesses the capability of, for example, recognizing like bacteria or other like harmful entities, and secrete some peptides that act as antibiotic. These are the defensins, and the defensins are able to exert an antibacterial activity. This is known as innate immune response, because every person, maybe also animals, they can do this, so they can try to defend from bacteria by themselves, by their skin. But when the skin is damaged and we have a wound, sometimes it's difficult to have self-repair. So it depends, because we have several types of wounds. So surface wounds can self-repair, but when we go to full thickness, so the wound goes from the epidermis down to the hypodermis, or when we have complicated wounds like for diabetes and other immunodeficiency pathologies, then it's difficult for the skin to self-repair. So we have no more a protective layer, a full protective layer. We have some way that other bacteria can come and go into our organs. So, of course, materials in contact with the skin can have different applications. So can be used for repairing the wounds, can be used just for other purposes. We have still to remember that small size materials, nanomaterials, can enter into the cells. So this is something very important that we have to remember, because this is also the nanotoxicity is another important point that we have to face in this century. So when we develop materials for skin and other application, if we have biodegradable materials, it's better. And also because it depends on the shape of this nano-sized object, if they are like a very needle shape or they are spheres, so they can generate different inflammation and death inside the cells. So all these materials can be used for skincare products. So we have different types, cosmetics, personal care. So also we have biomedical products. So there are several properties that are important. And the materials can be used for treating some symptoms. For example, they can be used for the well-being, for cleaning, for some other for damaged skin, for some other pathologies or state that are like critical, so like wound, burns, and so on. So depending on the application, the best material must be used, and of course the more strict is the issue for the biocompatibility. Moreover, the need of skin change with age. So we start from, for example, babies when they have physiological factors, for example, the urines. Then with mature age, the skin encounters UV radiation damage, so this is more related to treating like cosmetic treating and well-being. And then we, in the end, in the aging, we go towards like other problems. For example, they are related to wounds or also urines. So it depends on the age. So by tuning our materials and the property of biocompatibility according to the age, we can also reach the most successful requirements. In the PolyBioSkin, we must focus on chitin nanofibrils. They are derived from crustaceans in the form of nano, so they lose their inflammatory properties, and we demonstrate that they possess good properties of immunomodulation and anti-inflammatory properties that are very important. Moreover, these nanofibrils have a lot of characteristics, can be combined with other other molecules. For example, with nanolignin, can incorporate some bioactive molecule, and we tried the glyceritic acid from glyceritia from plants. And also they are biodegradable by the human body by enzymes that we possess. So they do not generate any cytotoxicity and nanotoxicity issue. And here we have our paper that we publish. We also demonstrate that at this concentration, the complex of nanolignin and nanochitin could upregulate the expression of human beta defensin 2, so could let the cell be more proactive to fight bacterial contamination. So this is good to have in a biomaterial that is subject, for example, to stay in contact with the urines or to have some exposure to bacteria. And also we published several papers. I reported some examples in which we stress the importance of biocompatibility and skin compatibility on the three different pillars that we are investigating in PolyBioSkin project. So the diaper, the wound dressing, and also the cosmetic sector. So as I told in the beginning, it is important for the biomedical purposes, for the biomedical product, to comply ISO standards. And specifically, we have the ISO 10993 Chapter 5 that is related to the cytotoxicity, and also we have the Chapter 10 that is related to skin sensitization and irritation. So these ISO are mandatory for biomedical device. They are not mandatory to comply for devices that are not biomedical, as I told in the very beginning of this presentation. So the company don't need to comply these standards, but it is becoming also a necessity because to promote a product and to be sure that the customer has a good appreciation and no side effect by wearing like a product, even if it is not a biomedical device, the company start asking for this test, so they are sure that there is no inflammation process going on by being in contact with these new materials. So here I gave you an example in which we talk about the diaper, for example. So the adult products for incontinence, they are classified like a medical device because, of course, an adult person is not supposed to have incontinence. So this type of diaper must be certified, there are directives, must comply all the biomedical device requirement. But baby diapers and fem care product, because these are physiological condition, is not pathology, they are not medical device. So they don't have to comply to this standard by law. But as I told you before, now there is a new interest in also trying to understand if these materials can generate like a good reaction, for example, or if we can have a product that is widely appreciated by the customers. So how can we test this product to have so the satisfying results? We don't need to go to the animal. For some sectors, like the cosmetic sector, it is no more allowed in Europe to use animals, but there are very nice in vitro tests that can be performed in order to understand so some basic phenomena related to biocompatibility. These tests are they don't pose ethical problems, so they are very much appreciated. They are less expensive also, so it is a good tool to have a preliminary test. Now there is the skin equivalent, for example, to test cosmetic product, but we can also design more advanced tests by using the technology, the biological technologies available in order to, for example, understand inflammation. And this was a part of the work that we perform with the PolyBioSkin. So we set up a good model that is able to predict the inflammatory response by the keratinocytes from the epidermis. And also we set up a model of the dermis, which was more useful for sure to predict some in the interaction of materials in lesions like full thickness lesion and so on. So the floor is very open, and we can also relate the cells to the gender, to the age of the patient, in order to have always more and more complex tests that can give answers to the customers, to the company for the safeness of the company, of the customers. So this is what we have done with the PolyBioSkin, and we hope it was clear enough for all the attendants. Beatrice? Beatrice?
I'm not sure if we maybe have lost our host, Beatrice, now, but maybe we can just jump over this.
Yeah.
By the way, thanks, Serena, for the very nice presentation, and of course, Vitu Bari and all the others for the very nice overview on the testing possibilities at ISTM and all the technology insights into the details, actually what we could do with all your expertise at PolyBioSkin. So very grateful for that, and making sure that we had all materials at the properties that we needed. It was quite a long way, I have seen from the reports so